Hello class, welcome to day 23 of Coronachem, May the 6th, 2020. I'm at my parents' farm and I'll probably be staying here as long as I possibly can because I'm loving it. So yesterday I was going to give you the solution to a problem and I messed it up on the board, so I didn't show you. I just cut off the video at that point and I redid it. This is the danger of doing electrochemistry on the fly. You miss one thing and it throws the whole problem off. So I recopied the problem and I'll show it from beginning to end for you. So we have As2O3 reacting with nitrate to give you, I guess that's called arsenic acid and dinitrogen trioxide. I first isolated the two half reactions. So the As2O3 diarsenic trioxide turning into arsenic acid, and the nitrate turning into dinitrogen trioxide. So again, you follow the same procedure for balancing redox equations. First you separate the half reactions, then you balance the oxygens with water, followed by balancing of the hydrogens with protons, and lastly you balance the charges with electrons, and then finally you balance the half reactions using integers. So we're going to do that. So we have 3 oxygens on this side, 4 oxygens on that. But even before we start that, we notice that there's 2 arsenics here, 1 arsenic there. So that forces you to put a 2 over here. 2 times 4 oxygens gives you 8 oxygens, and there's only 3 oxygens on the left. So we're going to balance that by putting 5 waters. That creates an imbalance of 10 hydrogens on the left versus 6 hydrogens on the right. So we're going to balance that by putting 4 hydrogens on the right. And then lastly, you balance the charges by putting 4 electrons on the right, because there's 0 charges on the left, but plus 4 on the right. So you balance that off by putting 4 electrons. Now we can move to the second half reaction. There's 1 nitrogen here, 2 over there, so we're going to put a 2 in front of the nitrate. That gives us 6 oxygens versus 3 oxygens, so we're going to put 3 waters on the right-hand side. And then we'll balance the hydrogens by adding 6 hydrogens on the left. Then we balance the charges. 0 charges on the right, plus 6 minus 2 gives you plus 4 on the left, so we're going to put 4 electrons on the left as well. This allows us to add these half reactions without multiplying by any integers, because you have 4 electrons here and 4 electrons there. They cancel. The 6 hydrogens partially cancel with the 4 hydrogens, and you're left with 2. Water also partially cancels here, and you're left with 2 waters. Now we can write the net equation balanced under acidic conditions, but if you recall, I asked you to balance it under basic conditions, so I'll show you the last step for balancing under basic conditions, which I wasn't able to show you yesterday because I made a mistake and it would have been a disastrous waste of time to try to overcome it. So As2O3 solid plus 2H2O liquid plus 2 nitrates aqueous plus 2H plus aqueous gives you 2H3ASO4 aqueous plus N2O3. I'm gathering this is a solid, or is it aqueous? It is aqueous. AQ, and the waters cancel. So that's your balanced equation under acidic conditions. But how do we balance under basic conditions? Well, to balance under basic conditions, what you do is you add the same number of hydroxides as there are protons on the side that has a net amount of protons. So you have 2 protons on the left. I'm going to add 2 protons, 2 hydroxides on the left, and I'll do the same on the right because it's like an algebraic action. Whatever I do on one side has to be done on the other side to keep balance. And these 2 turn into water. So you'll have 2 H2Os here, and then there's 2 H2Os there. So that the net equation comes up to this. As2O3 solid plus 4 H2O liquid plus 2 nitrates aqueous yields two arsenic acids, AQ plus N2O3 AQ plus 2 hydroxides, also AQ, and now it's balanced in basic solution. Can somebody do me a favor and get me a drink? Ma mi daresti una bibita? Come quella che avevo lì. And so that was the homework question. So here it is balanced under acidic conditions. Thanks, me too. And here it is balanced under basic conditions. Just put my markers here. I've got a little drink. Good. Okay. Next, I'll continue with the notes where I left off from the last class, which was how to show half-cell potentials, I believe. Let me see if I don't recall now. All right, so on page 858 of your text, which you don't have, and so I'm going to draw it for you so that you do have a copy of what's going on. They ask, the two half reactions in a voltaic cell are zinc solid turning into zinc ions plus 2 electrons, and chlorate reacting to form chloride. I can't remember if I drew this for you, but I'll draw it now and then we'll be sure. And with chemistry, as you know, it doesn't hurt to repeat things because chemistry's hard, let's face it. I wonder if I can write on this board, will I? Let me take a little test. Oh no, not a good idea. Whoops a daisy. I have to clean that off later. Okay, so the practice example on page 858 is zinc solid turning into zinc 2 plus aqueous. And then the chlorate plus 6 hydrogens aqueous. So they've already balanced the equation for you, but what they want you to do is show and explain, I suppose, what it looks like in a cell. So we'll go through all that again if we haven't already done so, but like I said, it doesn't hurt to repeat a little bit. Okay, so there's your two balanced half reactions. Now let's show how is that going to play out in a cell. How would that look? So you'd have two beakers. Actually, these look more like buckets, but it doesn't matter. I'm not an artist, and you don't have to be. All you have to do is get the idea across. So there's your salt bridge. What this does is it provides a connection between the solutions that allows the equalization of the ions that build up. So if you have a buildup of positive charge on one side, positive ions will try to escape out of that solution by going into the salt bridge and going to the side that has a buildup of negative ions. So this allows equalization of the charges. Then you have an electrode dipping into the solution on this side and an electrode dipping into the solution on that side, and they're connected. And you could even put a little voltmeter on it to measure the voltage. Which in this case, I don't know if I even looked it up, because that's not what this is about anyway. So this electrode turns out to be zinc. This electrode could be platinum or graphite or some other metal that's not reactive. If you you can't afford platinum, you could always use stainless steel, because stainless steel has a high oxidation potential. It's an alloy precisely made because it doesn't undergo electrochemical reactions easily. You don't want, for example, your cutlery to rust when you wash it. So what they do with stainless steel is they mix iron, cobalt, and nickel in the right proportions so that it creates an alloy which has a very high resistance to corrosion. So then you can put your forks in a dishwasher and they won't rust. So graphite or platinum or some other non-reactive metal, you can even put stainless steel. Okay, and that's so that the reaction can have an interface to take place, because there's ions in the solution here which are going to react. So for example, the chlorate on this in this solution is going to touch on there, and what comes off is going to be chloride, because the electrons are going to reduce it. And look, the electrons are moving this way. Okay, this is called the anode. The anode is always on the left. You always draw the anode on the left. You always draw the cathode on the right. A good way to remember it is do it alphabetically. Anode left, cathode right. Anode has oxidation, cathode has reduction. Both start with a vowel, both start with a consonant. Perfect way to remember it. So this is a piece of zinc dipping into the solution that contains water and whatever other salts are necessary to promote the reaction. What happens here is the zinc actually comes off. The anode gets lighter over time, and you get zinc ions forming in solution and electrons going this way. So electrons are leaving the zinc electrode as the zinc ions also are leaving the surface of the zinc electrode. So the zinc ions go into the solution, so this solution here to there, say, and the electrons that are left behind with the zinc travel through the wire to the cathode, and the cathode is written as positive and the anode is written as negative. So the negative charges here are appearing because the electrons are being deposited, are being left away by the zinc. They're being given up by the zinc, which is undergoing oxidation. And the cathode is undergoing reduction. To reduce something, you have to provide electrons. So where are the electrons coming from? They're coming from the other side. They're traversing on the wire, and they're appearing here, where they then reduce the chlorate. So what happens here at the cathode is the chlorate, which is aqueous, is turning into chloride, which is also aqueous, and 3 waters. On the other side, you have zinc, which is a solid, turning into zinc ions and 2 electrons. All right? So the anode is consumed, it gets lighter. The cathode may get heavier depending, in this case it wouldn't, because both of these things are going into solution. This is chloride, sorry, that's a negative. So in this case, it approaches the cathode, gets reduced, and what's released is chloride. Give it some thought, on page 859, the book asks, which zinc atoms in the strip of zinc metal are primarily involved in the redox reaction with copper, with cupric ions? The surface zinc atoms or the interior zinc atoms? What do you think? Obviously, it's the stuff on the surface because it has to be at the liquid-solid interface. It's not the metal inside the piece of the electrode that's going to react. It's the stuff on the surface. Okay? Now, what is EMF? They mention EMF in the chapter. It means electromotive force, and I'll write it down for you so you will know. Oh, this board erases like a dream, except for the places where there was tape. Now, when they mention these voltages that you look up at the back of the book, you'll notice that they are
measured at 25 degrees Celsius. Everything has to be done under standard conditions. What do they mean by standard conditions? It means that all the chemicals involved are at a concentration of 1 mole per liter. The temperature is 25 degrees Celsius and at 1 atmosphere pressure. If you change the conditions, you're going to get a different voltage. And the book explores that later on, but that's beyond the scope of this course. Right now we're just introducing you to electrochemistry. Next year, we're going to go into that. We're going to go into this idea that you can actually change the voltage of an electrochemical reaction by increasing the pressure, changing the temperature, or even the concentration of the various chemicals. And there was a German chemist by the name of, I think it was Walter Nernst, who derived an equation that recognized this fact that electrochemical reactions change the voltage if you play around with the conditions. And it actually can give you the means to make a battery just by you can even have the same half cell but different concentrations, and I'm getting carried away, so let's continue with the regular lesson.
So cell EMF under standard conditions. One volt is equal to 1 joule of energy per 1 Coulomb of electrons. What's that, Coulomb? Well, okay, let's do one thing at a time. 1 joule of energy imparted to 1 Coulomb of electrons. Okay, what is a Coulomb of electrons? Why do they use this word?
The Coulomb is a unit that was derived in honor of Charles Coulomb, who was one of the first guys to discover the charge, the effects of static electricity. He discovered that using little cork balls, he calculated how much attraction there was between two cork balls that were held at a certain distance apart. And it was such a very delicate experiment. He used a horsehair to measure the tension. So imagine using a horsehair as a tensiometer. In other words, how much force did it take to twist the horsehair? And that was how he measured the attraction between the two cork balls. So it was the man was very refined. He invented a great experiment, and this is the essence of genius. You look at something that everybody else looks at. You know, they discovered back 2,000 years ago that if you rubbed amber, it could pick up little bits of paper. Stuff was stick, and we've all noticed that when you rub a balloon, it sticks to the wall. Why does that happen? It's because electrons are stuck to the material, and when there's electrons stuck on a material, they repel each other, and they repel the electrons on other materials. So that's why they can either stick or they can repel each other depending what you do. Because sometimes when you rub one material with another, one material will take the electrons away from the other material, and then the material that lost electrons ends up having a positive charge. So it'll be attracted to things with a negative charge, but if you take two things with positive charge, they'll repel each other, or if you take two things with a negative charge, they'll repel each other. So that's a whole chapter on electrostatics if you're taking physics, and there's a whole bunch of laws around that, and that's not where we're going. What we're looking at is how much energy can electrons carry? And this is what the volt is all about. The voltage is a measure of how much energy the electrons are carrying. And there's another measurement that's important, and that is how many electrons are passing by a certain point in a circuit or in a wire, and that's called amperage. So you could have a rough analogy. The amount of electrons is roughly analogous to the amount of water passing by in a river. More water means more current. And more electrons also means more current, and that's measured in units of amperes. On the other hand, you could have the water going slowly, or you could have the water going fast. That's not a good analogy. Let's talk about the height of a waterfall. You could have water falling from a very high height or water falling from a low height. That's the amount and that gives the water potential energy. And then after the water falls, it has kinetic energy. So electrons can have high energy or low energy. If you want to push a lot of energy through a wire, you can pump up the voltage to a very high level, and then you'll be able to carry a huge amount of energy for the amount of current that's going through the wire. That's why if you want to power a whole city, you'll have what are called high tension power lines where the voltage can go as high as 750,000 volts, which is why you don't want to be getting anywhere close to those power lines, and that's why they put them way high up on towers so people don't touch them. In fact, you don't even have to touch them. Just get within 2 feet of them, they can shock you. Just the electricity will jump out of the wire. So it's good not to stay anywhere close to those kind of things. So anyhow, the volt is the amount of energy that is carried by a joule of by a Coulomb of electrons. What is a Coulomb? Well, 1 Coulomb equals the reciprocal of the charge on 1 electron. So let me just look that up so you get an exact number on the phone. Has this embedded in the memory. It is, I think it's number 19. No, it's not. It's number 9. So alpha constant 0.9. That is the charge on 1 electron. Okay, so 1 electron has a charge of 1.609 times 10 to the negative 19 of a Coulomb. So it's a measure of electrical charge. Or you could say 1 Coulomb, if you take the reciprocal of that number, it'll tell you how many electrons there are in 1 Coulomb of electricity. So 1 Coulomb is equal to 6.24 times 10 to the 18 electrons. Okay, if you take that many electrons, you'll get a charge of 1 Coulomb. And there's another unit that gets involved. It's called the Faraday, in honor of Michael Faraday, because he was the first one to do experiments on electricity. And if you take about 96,000 coulombs, it equals a mole of electrons. And that's 96, it's called a Faraday, in honor of Michael Faraday. You only have to know that much. Now, cell potentials, also known as electromotive force, are reported in voltages. The voltages are measured under standard conditions, like I said earlier. Basically, 1 mole per liter concentration of everything at 25 degrees Celsius and 1 atmosphere pressure. So, all cell potentials, I should say all standard cell potentials, and they have a special symbol for it. They say E naught. They put a little 0 at the top, like a degree symbol, and that means it was done, meaning it was measured at 25 degrees Celsius, 1 mole per liter concentration, and 1 atmosphere of pressure. So all those conditions have an effect on the voltage. So if you take a electrochemical cell and you go to the bottom of the ocean 7 miles down where the pressure is 14,000 pounds per square inch, it'll change the voltage on the cell. I don't know how much, but it will have an effect. Also, if you raise the temperature of a battery, we all know this, if your car battery goes to minus 20, it doesn't work anywhere near as well as when it's at plus 20, because all chemical reactions tend to slow down when you lower the temperature. So that's why we say E naught, because it's important to know what the conditions are, because the conditions will affect the voltage. So cell potentials on page 861, the book asks, a certain voltaic cell has a standard cell potential of 0.85 volts at 25 degrees Celsius. Does this mean the redox reaction of the cell is spontaneous? And the answer is yes. If the voltage is positive, the reaction happens by itself. If the voltage is negative, what it's really telling you is the reaction likes to go the other way. It's the opposite of the way it's written. So typically when we do electrochemistry, we write everything in half reactions. We do 1 half reaction, which is a reduction, and the other half reaction, which is an oxidation. You combine those two together and you get a cell, because one reaction has to give up electrons and the other one is going to take the electrons. Otherwise, you don't have a redox reaction. Okay, so
how do they get the voltages? That's the next question. Well, what they did is all the scientists got together and they agreed that they were going to call one of the reactions equal to 0.
So they used a simple reaction, and they call it the SHE, the standard hydrogen electrode. SHE for short.
The following reaction was arbitrarily assigned. Arbitrarily means they all got together and they decided.
To arbitrate means somebody judges.
Arbitrarily. So they said this reaction, it has 0 volts. And then they compared all the other reactions to it. You'll notice that hydrogen is kind of in the middle when it comes to voltages. It's, here's a good word, ambivalent.
Really, I think you should say the word ambivalent. When somebody is ambivalent, they're undecided. Do you want to go to see a movie or you want to go to dinner? I don't know, I'm ambivalent. You decide. Okay, so hydrogen is also ambivalent. If you put hydrogen with a metal, it will behave like a non-metal. If you put hydrogen with a non-metal, it behaves like a metal. So depending on what the voltage is of the substance that you mix it with, the hydrogen will adapt itself because it's kind of in the middle. And that's why they gave it a voltage of 0, because it falls in the middle of the range of voltages.
So again, the conditions here are 1 molar, standard conditions, and 1 atmosphere gas.
So what they do is they bubble hydrogen gas onto a platinum electrode at 1 atmosphere pressure. That causes an electrochemical reaction. So if you put a platinum electrode in acid with a 1 molar concentration of protons, the protons will pick up electrons and you'll get hydrogen gas. And to make sure that the cell is working properly, they have gas bubbling at 1 atmosphere pressure through the solution to maintain that pressure of hydrogen gas at 1 mole. Okay, so
all other cell potentials, all other half cell potentials are defined relative to the hydrogen half cell. Made of platinum wire in aqueous solution with 1 molar H plus concentration. And that's called the standard hydrogen electrode.
I'll cut it off at the half-hour mark. I'm just going to say that because
tomorrow I'll spend the whole lesson explaining to you how half cell potentials are
all written as reduction potentials, usually.
so tomorrow this is what we're going to address. Most of the time half cell reactions are written as reductions. Guys,
Your advice for today, your homework for today, is, if you haven't already done so, and I know some of you haven't, watch the first 6 parts of my electrochemistry playlist. If you don't do it, don't complain you don't know what's going on, because you won't. That's a guarantee from me. Watch those 6 playlists, and we'll see you tomorrow. Bye-bye.